Hi everyone. So for the homework, you had, I think, one question about potential energy. Well, I don't know if potential energy, but just springs. And we did not explicitly talk about this or implicitly. But I did say that potential energy was not exclusive to gravity, right? Although we have been using gravitational potential energy as potential energy, uh, which is to say that anytime we said potential energy, we meant gravitational potential energy. Now we're going to learn about another type of potential energy, which is of a spring. Um, you can think about shock absorbers for cars or pinball machines, any spring that you have, or think about the plunger cart, right, for lab 2. Remember I told you we needed the plunger, and then you saw the spring kind of absorbed the impact. So we're going to learn how this works, okay? And this example will help you with the review as well. It says, a spring with spring constant of 350 newtons per meter is stretched 20 centimeters from the equilibrium position. A. Find the work done. B. If an additional 8.75 joules of work are done to the spring, find the corresponding distance. There's, I think, a few things we have not defined, or maybe you don't know what they mean, but don't worry, we're going to do just that. And then we have been given a hint, that is the potential energy of a spring. That's why I have that little s for spring. And it is 1/2 kx squared. It looks very similar to the kinetic energy equation, right? 1/2 mv squared, with different letters. Now the k, that is the spring constant. Okay, so I think we should highlight it and then define it. So spring constant, that is the letter K. So K is spring constant. What this is, I think, let me use, instead of a equal, just an arrow. The way I teach it is, this is a property of the spring, which is the stiffness of the spring, right? How stiff it is. And this number, what it means is it takes 350 newtons of force to stretch or compress this by 1 meter. That's what it means. So it's the spring constant. Again, the property of the spring, which is the stiffness of the spring. Spring constant. And then the x, and this is the distance, right? Over here. That's what it means. X is distance. Let's just blue. And then blue here. Distance. And then I'm just going to say, if you stretch or just do compress the spring, that's what it refers to. And I think that's it, right? So now that we have to find these things, right, spring constant and the distance, we can start with the given, and we're going to start with question A. So the given is pretty straightforward. We have the spring constant K of 350 newtons per meter, and we have distance of 20 centimeters. Notice how the unit is Newton per meter, so we have to convert this into meters. Now, centimeters, the prefix centi, that is times 10 to the power of -2. Just hopefully you remember that 100 centimeters equals 1 meter. So if we go from centimeter to meter, we move the decimal point 2 spots to the left because 100 has 2 zeros. So that'll be 0.2 meters. And that's it for question A, right? So let's just do A. One thing that I want to add is the fact that we're starting from the equilibrium position. Although we could solve this problem just by using these numbers, I really want to emphasize the fact that we have the equilibrium position as our starting position, because that will help us with question B. What it means is we're starting from equilibrium, and when we start from equilibrium of a spring, we assume the initial position to be 0 meters. Again, you'll see why this is helpful. Not yet, but you'll see. So again, anytime you have starting from the equilibrium position, that is x initial is 0 meters. We need to find the work done. And we learned two definitions for work, one with force, one with one with force and one with energy. In this case, we want to use the energy, and the reason why is the hint says use potential energy. So we said that based on the Work-Energy Theorem, work done or net work is the change in kinetic energy. And then we added a few things by saying that anything that leads to kinetic energy. And then for this one, we can get away by saying that the work done will be the change in energy of the spring. And we know that the spring has potential energy. Therefore, the work done will be the change in potential energy of the spring. Okay, so now let's use that equation over here. So delta, that is change, means final minus initial. So then the work done will be the potential energy of the spring. I'm going to omit the S because that's we're using just the spring. Potential energy final minus potential energy initial. And if you think about it, based on this equation, the spring constant is a constant, meaning it will not change. What will change is the distance, x. So to account for final and initial, I need a final x and an initial x. That's why I wanted to add this x naught over here. So the work done will be potential energy final, that is 1/2 k x final, so just x squared minus 1/2 k x initial squared. Again, I know x naught is 0, so I technically didn't need to state this initial position. Again, I'm just showing you this because it'll help you with question B, okay? So just bear with me. Since x naught is 0, this whole thing will cancel. And then we have that the work done is 1/2 kx squared. Now we are ready to substitute. So work done is 1/2 spring constant, which is 350 newtons per meter, times the distance squared, that is 0.2 meters squared. And let's solve it real quick. Question A is rather simple. 350 for the spring constant, 0.2 squared. The answer is 7. 7 what? This is work done. Change energy, so 7 joules. Okay? So work done. I am not following significant digits. I should, but I'm not going to do it. Sorry if I offended anyone. So 7.0 joules. So now we're done with question A. So let's box it. Let's continue with question B, right? It says, if an additional 8.75 joules of work are done to the spring, find the corresponding distance. Now I'm going to use the picture. So let's say I'm going to call this point A, point B, right, to account for the distance. So from the equilibrium position, which I'm going to assume is like somewhere here. So from here to here, let's think that's A, right? This is from equilibrium. Again, I'm just assuming the equilibrium position is here, maybe a little bit lower, make it a bit more realistic. And then, so this is equilibrium, right? And normally we show equilibrium position by a dotted line. So I'm just going to make a line that matches this one. And I'm going to make it dotted. Well, it's just the eraser. That was a lot. Let's see. Whatever. There you go. That's the equilibrium position. Okay. So we know from here to here, this is point A for question A, that is 20 centimeters. Now, if an additional 8.75 joules of work are done to the spring, so once it's stretched to this position, we have 8.75 joules of work done, then this stretches a little bit more, which is the distance from here to here, this one. So this is what we're finding. This is the corresponding distance at point B, right? So this distance is what we're finding. So we have two ways, or there's a couple ways to solve this one, to find that corresponding distance. The first one would be taking your initial position to be 0.2 meters. So x0 would not be 0 meters, but 0.2 meters. And then your final, just x, the one we're looking for, right? So that would be one way to do it. So let me just, I'll keep using red to show you, right? So let's write, well, I'm going to use green to show that we're working on the question B. And so in this case, I could use x initial to be 0.2 meters, x final to be what I'm looking for, and then my energy, or the work done in this case, would be the 8.75 joules. And I could find x naught by using this equation, right? So I would have this, because the spring constant is the same. But the math, because I did it both ways, it's a bit more complicated if you do that. Not that much, right? But just a little bit. So I'm going to show you a different way. Again, both of them work. I just want you to see that when we find x, that is not the answer. Meaning, when we find x, that's not the corresponding distance. That is the total distance. So truly, what we're finding here is delta x. That is the corresponding distance, the distance from A to B. Okay? So let me show you the other way. If I consider the equilibrium position to be 0, so in this case, x naught, wait, there you go, x naught to be 0 meters, I'm still looking for X final. But in this case, the work done, which is the change in energy, the total change in energy, is not only the 8.75 joules, but the work done that it took, or the energy required to go from 0 to 0.2, and then from from 0.2 to this distance, which is 8.75 joules. What I'm trying to say is, for this one, when I have x naught over here, and this is x, this change, this distance, right, will require a change in energy or work of 7.0 joules plus 8.75 joules. That is the total work done, which will be 15.75 joules. Again, both of these work, but I think this is easier in the mathematics. You'll see why. And then I'll just rewrite my spring constant, which is 350 newtons per meter. Okay. So I'm going to use this equation. I'm going to write it again. So I know that my work done is 1/2 kx final squared minus 1/2 kx initial squared. And I know that my x initial is 0, therefore I can cancel this term. The difference on this option, right, the one I wrote in red, is x naught would not be 0. So you would have to, you can't just cancel it. So you have to include this in your algebra. If you want to do it just for fun, that's cool. You get the same answer, well, the same x. But just because I don't want you to be watching this video for more than 30 minutes, because I mean, who does, right? I'm going to use this version, right? So then my work done is simply 1/2 kx squared. And I cannot substitute just yet because what I'm finding is x. So let's solve for x. The first thing I'm going to do is get rid of this 1/2. So I multiply times 2 both sides, as you guys know. I'm going to flip my equation, so I have kx squared equals twice the work. We divide by k, which is the spring constant. So this cancels. Now we have x squared equals twice the work divided by spring constant. And to get rid of the square, we take the square root. Again, this will cancel. So my final equation is x final equals square root of this one. You need to make this smaller, right? So it fits. There you go. Now I can substitute. So over here. X equals, I'm going to do the square root at the end. So twice 15.75 joules divided by the spring constant, which is 350 newtons per meter. Then I take the square root. Whoa, I'm just going to use a line. I'm not going to be able to do it straight. That's for sure. There you go. Extend this one a little bit. Let's do one more. Gonna make this smaller so it looks okay. There you go. So let's try it. Driving the square root. Let's use parentheses. Another parentheses. So 2 times 15.75 divided by 350. That's for the spring constant. And we have 0.3. That's x final. X final equals 0.3 meters. Again, this is not the answer. We're trying to find the corresponding distance, the additional stretching, which is delta x. Now for this one, right, and I'm going to use blue. So now to find delta x, we have to consider x naught to be 0.2. Again, if we had used this version, then I wouldn't have to specify what x naught is because it would be the same. But just for the simplicity of mathematics, I got the final distance. And to find delta x, I need x naught to be 0.2 meters, right? So I'm going to use this one, blue x naught, right? So you know this is for this one. And my final x is 0.3 meters. Delta x is x final minus x initial. I'm not even going to substitute. You guys know what this is. So corresponding distance, delta x, is 0.1 meters. So by stretching an additional 0.1 meters, we had an additional 8.75 joules of energy. And there you go. That is it. Don't forget, this is the equation that you want to use. Don't forget that work is the change in energy, at least for this for the spring. And make sure you know which distance or distances you're going to consider. If it's from equilibrium, if it is from a ready stretched position. Again, if we had used this setup, it would have been x would have been the same. Just work done would have been a little different, and we would have had an additional term over here. That's it, guys.